Okay, good evening, everyone, and welcome to the latest installment of the SLAC Public Lectures. Today we're going to have Dr. Jerry LaRue, who's going to talk about, well, I'll tell you in a moment. Let me just say first that, as you see, there's a building going up across the way, and it's not going to be ready for the September public lecture, but I think it looks likely it will be ready for the November public lecture. In there's an auditorium double the size of this one. So tell all your friends. It'll be happening then every 2 months, starting at the end of November over there. Is this microphone? I'm not close enough. Yeah. Okay. For tonight, we have Jerry LaRue, who I guess started out as doing his undergraduate work at Willamette University up in Oregon. He then came to UC Santa Barbara to do a PhD in physical chemistry. As I understand, sometime in his early education, he learned what quantum mechanics was, and it changed his life. So he did a PhD in chemistry. He came here to SLAC to join the actually many different efforts here to understand how atoms, molecules, and electrons interact on the femtosecond timescale. That's a millionth of a billionth of a second. And so now he'll tell us a little about that, watching chemical reactions in action. So Jerry, thank you very much.
Thank you. Thank you for the introduction. It's a pleasure to be here speaking. I've always wanted to give a public lecture here at SLAC, so I'm happy to have the opportunity too. I've been at SLAC now for 4 years, and today I want to talk about what I've done in those 4 years, which has really been about trying to understand the most fundamental, basic aspects of chemical reactions. Here's a map of SLAC. We're over here in the red. I've been working on my office here now, and all these experiments took place across site over here in what's called the near hall at the Linac Coherent light source. I'll get back to that in a bit. So I really want to understand how chemical reactions work. I wasn't really always interested in chemistry. In fact, in high school, the most important thing was simply how far I could throw a shot put. I really didn't like chemistry. I only took chemistry because a friend told me you got to make candy in the class. So when I was going to go to college, I asked my older sister for some advice. I said, what classes should I take? And she said, take chemistry, it's a must. It's a base science that allows you to branch out into any other field of science. And so I took her advice, and before I knew it, I accidentally became a chemist. And ever since then, I've just absolutely loved chemistry. And chemistry is controlled by the laws of quantum mechanics, which is unfortunate. Well, first let me back up a second here and say the reason why I got interested in chemistry. I first started to get really interested in chemistry because it's a tool that allowed us to understand the world around us. If you want to know why the sunset is red, or maybe the different life that goes on in a river, chemistry can tell you all about these different processes. And so it's a tool for us just to really understand our surroundings. But we also want to use chemistry for our own purposes. And it's controlled by laws of quantum mechanics. And this is where, if you don't know quantum mechanics, it's a very tough laws of physics. In fact, it's so tough that we only can really understand the hydrogen atom. Absolutely. So if we want a reaction to occur, we can't just simply tell the molecules to react. We have to figure out ways to get them to react even when they don't want to. And this is the essence of where my research has come in. And we get the chemical reactions to react by using what are called catalysts. These promote certain reactions. Now, catalysts are found everywhere. In fact, life is based upon catalysts. Life uses enzymes which are catalysts to make the important chemical reactions that sustain life here on Earth. But we've also learned how to use catalysts as well. In agriculture, we need to produce a lot of fertilizer in order to sustain the world's population. The main ingredient of fertilizer is ammonia. So we have to use a catalyst in order to produce enough ammonia to really grow all the crops that we need to grow. And there's many, many examples. If we want to talk about fuels, carbon neutral fuels, which are the fuels of the future, we need catalysts in order to promote the reactions in order to synthesize these important fuels. Plastics, all the plastics that we use in our everyday lives, They use catalysts in order to make these plastics. And pollution control, both to prevent pollution from going into the atmosphere and the environment, but also to take it out as well. And these processes use catalyst. So what is a catalyst? Well, if we go to a chemical reaction, here on the left side we have the reactants, and on the right side we have our products. You can think of it as a hill. We want to go from our reactants, A plus B, to our products, AB, and we have this hill in the way, this barrier. And so the reactants, they need some type of push in order to get up over the hill. The top of the hill is a very unstable state. It's called a transition state. It's been thought for many years that we'll never be able to see the transition state because it's very unstable. Molecules don't want to be there, but they have to get over that state. And once they do, they can roll down into the products. Well, the catalyst comes in, it lowers the energy to the transition state. It makes it easier so we don't have to push the molecules as hard in order to go from reactants to products. So it makes the reactions more efficient. And oftentimes, the catalyst here that we use in a lot of important industrial reactions, they use a metal, the surface of a metal. And so where my research comes in is I want to really understand what happens on the surface of these metals on a catalytic surface in order to push the reactants or the molecules from the reactants into the products and understand all the steps along the way. And the one that I'm going to focus on for the majority of the talk is a specific reaction, and it is involved with the catalytic converter, which you may know from your car. It's probably one of the most common catalysts. What a catalytic converter does is your engine exhausts all of these gases. You have what are called nitrogen oxides, where you have a nitrogen atom and an oxygen atom, or a nitrogen atom and two oxygen atoms. These play a big role in creating smog and acid rain, so they're not very nice molecules. We have carbon monoxide, which is one carbon bound to one oxygen. Carbon monoxide is toxic to humans when we breathe it in, so that's also not a very good one to have around. And lastly, we have, I denote here, CH. This is just the unburnt fuel from your engine. The engines are 100%. You do get some unburnt fuel that does come through, and these are not so very good. These are not good for the environment. And so we want to get rid of all of these. And the catalytic converter does a very good job of that. The catalytic converter will take the nitrogen oxides, and it will produce from that nitrogen gas and oxygen gas. The atmosphere is made up of 99% of these two molecules. So they're pretty good molecules. The carbon monoxide will react with oxygen gas to form carbon dioxide, where it's one carbon and two oxygen atoms. Now, carbon dioxide is a climate-changing gas, so it's not that great, but it's not toxic to us, which does make it the lesser of two evils. So we do prefer carbon dioxide over carbon monoxide. And lastly, the unburnt fuel goes into the catalytic converter and gets converted also into carbon dioxide and water. If we were to really zoom in on the catalytic converter and punch a hole and look at it, what we see is a very high surface area covered with metal catalyst. And the metals often used are platinum, palladium, and rhodium. And if we were to zoom even further in and look on the atomic level to see what's happening, and this is where I'm really going to focus on most of the talk now, on specifically reacting carbon monoxide with oxygen to form carbon dioxide, what we would see is that the carbon monoxide and oxygen molecules, they stick to the surface of the catalyst. Carbon monoxide is unaffected, just sticks straight up. The oxygen molecule dissociates. It separates into two individual oxygen atoms, which we call atomic oxygen. On the surface of the catalyst, one of those oxygen atoms and the carbon monoxide will then react to form carbon dioxide, and carbon dioxide will leave the surface. Sounds pretty simple, but the big problem is there's a lot going on in that step of going from carbon monoxide to carbon dioxide that we want to understand, and so far we don't really understand what's going on. And you could ask one question, so what? The catalytic converters are old technology. They've been around since the 70s. They're very good at what they do. Why do we really want to look at this reaction, this old reaction? Well, there's two good reasons, and these reasons aren't specific to just the catalytic converter. They're pretty general for most catalysts that we use in industry as well. And the first one is cost. Sometimes catalysts are very expensive. In fact, platinum, palladium, and rhodium are not the cheapest metals. They're very expensive. There's been numerous cases where catalytic converters are stolen just so people could take the metals inside and sell them. And the second one is energy or temperature. Oftentimes, these reactions require extreme conditions, such as high temperature, in order for us to actually get the reaction to go forward. the catalytic converter in your car, the first 5 minutes that you turn your car on, it doesn't really do anything. It becomes only active at high temperatures, and so you have to wait for that engine heat to heat up the catalytic converter in order for these reactions to proceed. And if the fuel efficient standards get tougher and tougher, the engines will produce less heat. And it's estimated that sometime in the 2020s, current catalytic converters just won't even reach a high enough temperature in order to facilitate these reactions, in which we have to start heating the converters themselves, which is an energy cost. And so we'd like to move beyond the cost issue and also the temperature or energy issue. And to do that, we need to understand what's happening on that surface. And so we can start by kind of conjecturing, well, what does happen? What specific processes can happen on a surface of a catalyst? First one, if a carbon monoxide comes to the surface of a catalyst, the reaction takes place on the catalyst. So the first question is, will that molecule even stick? If it just bounces off or sticks for a short while and desorbs, which is called desorption, then it's not going to have too much effect on the reaction because it's not present on the catalyst. If, on the other hand, it adsorbs onto the surface, which means it sticks to the surface, then the reaction can proceed on our surface. The second step is energy transfer or temperature. Chemical reactions are all about energy and temperature, and we want to know how the energy and that temperature, what happens to it, how is it transferred during the course of a reaction. The third is location. The entire surface area of a catalyst is not entirely created equal. Location matters a lot to the chemistry. If you have a carbon monoxide sitting on top of a single catalyst atom, oh, what happened here? All right. That chemistry, if the carbon monoxide is sitting on top of a single atom on a catalyst, that chemistry can be very different if it's now next to two atoms on your catalyst, or if the molecule is standing up versus laying down, or even if the molecule is on some type of edge or cliff. The chemistry will be very different between these four different combinations. And so we want to know where are the reaction, or where are the chemicals during the course of a reaction. And lastly, of course, chemistry is all about making and breaking bonds. We need to pull apart pre-existing bonds, pull those molecules apart, and then bring the other molecules together in order to make new bonds. And so we want to know what exactly is being broken or made throughout this process. So the system we're going to look at today is carbon monoxide reacting with oxygen to form carbon dioxide. And the catalyst that we've chosen to use this system to study is ruthenium. Now, ruthenium is a very nice catalyst for this because ruthenium has the property that under certain conditions, it's not active at all. Under other conditions, it becomes very active. And so we can use this in order to set up our system without it reacting and then push it so that it starts reacting all at one time. And how do we do that? So we have here the reactants and the products, and if you were to look at the catalytic converter in your car during a chemical reaction, you would see reactants, you would see transition states, products, you would see everything all along here at once. The reactions are happening at different times. We want to start it all at once. The way to do that is to use a laser. And so on a ruthenium catalyst, we have the sample cold, so nothing happens, and we heat it with a laser. And this gets the reaction going and pushes everything all at once. Now the laser is nice because it's fast. We use laser pulses that are less than 100 femtoseconds. What does that mean? Well, 100 femtoseconds is 0.1 picoseconds, or it's 1 times 10 to the minus 13 seconds. So it's a very, very small number. To give you an idea of how small that is, if you were to shine a laser from the Earth to the moon, it takes light about 1 second to travel that distance. In 1 times 10 to the minus 13 second, light has enough time to travel the width of a human hair. And so this is a very, very small time frame that we want to look at in these chemical reactions, and we have to because that's the time frame that chemical reactions occur at. So we heat the surface with our laser. Now that brings us to a question of what is temperature. We talked about temperature in everyday life, temperature and heat, but what does that mean when we're looking at the microscopic level? What is temperature on the microscopic level? Temperature is motion on the microscopic level. A lot of it is motion. The molecules are vibrating. or they can rotate. They can fly through space. If you were to take a piece of ice and put it in your hand, it feels cold because heat or energy is transferring from your hand to the ice cube. The molecules in your hand, which are vibrating fast, are going to start to impact the molecules in the ice and start to make them vibrate and move. And soon enough, those molecules will have enough energy that they can break away from the crystal structure that they're in and become liquid, and the ice will melt. And so a lot of times, temperature is simply motion. Now, on a catalyst, you can think about a catalyst, you have a lot of atoms closely packed together. So on this ruthenium catalyst that we look at, this metal catalyst, we have a lot of these atoms, they're close together. That's really going to impact how free they can move. And so when you heat a surface, a ruthenium catalyst, for example, you get a slightly different motion. It's called phonons. And that's when all of the atoms in the surface are moving together in a concerted motion, like a symphony. And this is essentially the temperature, or this plays a big role in temperature of the catalyst. The more you heat it up, the more phonons and the faster these phonons are going to move. But temperature is not just motion. Motion's a big part, but we also have to look at the other aspect of temperature as well, and that's electrons. So every atom is made up of a nucleus at the center with electrons that orbit around the nucleus. Now these electrons, they have temperature as well. If we look at a metal catalyst, so this is a single individual atom. Now again, we look at a catalyst here, a metal catalyst, and we have all of these really closely packed electrons together. Well, because they're so close, we can no longer really think of just single electrons around a single atom. We now have to look at a bath or a bucket of electrons. They're all mixed together. So we have our catalyst here, and we have a bucket. And when it's cold, you can think of this as being a calm day at sea, where the sea is very glassy and calm and smooth. What is this? All right, so when the system's cold, we can think of all these electrons as being a smooth day out at sea where we have a glassy surface sea. When you heat it up, the electrons you can get some very high energy electrons. They can increase in energy. And you can think of this like a tropical storm where you now have these big, giant swells and waves. Well, electrons behave very similarly. You have these very energetic electrons. And so temperature is really a combination of this kinetic motion and the electrons. And this is important to keep in mind when we talk about laser heating of a surface. And here's why. Because when you heat the surface with a laser, you get laser chemistry. Here we have our surface, our catalyst, and we put oxygen and carbon monoxide. When you first excite the surface with a laser, an interesting thing happens. Only the electrons get excited at first. Your molecules in your catalyst, they don't change. The motion, the kinetic motion doesn't change. It's only the electrons that change at very first. Now these electrons are fast. Electrons are much, much faster than motion, or than the molecules themselves moving. And so these electrons can induce some type of chemical reaction. And if they do that, this process is going to be really fast. It's going to be on the time scale of the laser excitation itself. Less than a picosecond, maybe 100 femtoseconds, 200 femtoseconds, essentially the width or two of a human hair in time. But if nothing happens, or if we wait a bit, those electrons are going to lose energy, and that energy is going to go into the catalyst. And it's going to start causing the atoms in the catalyst to start moving, this phonon motion. And this phonon motion, it can cause chemistry. You can think of this as a way that in order to react to two molecules, you have to bring them together. And so if they have more energy, more motion, they can collide with each other. And after enough collisions, maybe the carbon will react with the oxygen, and you'll eventually form the molecule that you want. And so both of these processes can happen where you can have electrons that do the chemistry, you can have the phonons, or the motion, the kinetic energy, do the chemistry, or you can have a combination of both that do the chemistry for you. So now we have our surface, we know we heat it up, and we know we get our products. And as I said from the beginning, what we really want to do is understand what's happening on the surface, on the atomic level, the most fundamental processes that are happening. And to do that, we need a camera. Our camera in this case is X-rays. X-rays here at SLAC. So if you think of a reaction that's going in time, you start with your reactants. Your reaction goes, and maybe you make some products or some molecules that aren't your final product. These would be called intermediates, and you have your transition states and everything else that goes along during the course of the reaction, and then eventually you start to form your products. And we want to really elucidate this process and see what happens during the chemical reaction. And so to do that, to think about how we can use X-rays as our camera in order to look at that, we have to return back to the atom. Now this is the Bohr model of the oxygen atom, the same one I had up before, where you have the electrons orbiting the nucleus. I just want to point out that even though this model is very nice, it's very simple, and it definitely helps in understanding chemical bonding, this is not actually what electrons look like. Electrons don't orbit a nucleus like the planets orbit the sun. Instead, what you have is you have these different shells, and each shell looks differently. So the shell closest to the nucleus, which we call the 1s, is a sphere of electron cloud. It's just a round sphere of electron cloud. If we go out further to the 2s, one further out, we start to see that the sphere of electron cloud gets bigger. And if we go even further out to the 2p orbital, then you start to see different shapes. You see lobal structures as well, and this is just electron cloud density. So the electrons are a little bit more complicated than what's shown in this picture, but this picture is great in its simplicity. It really shows the highlights of what a chemical bond is. And so here we have oxygen atom and a carbon atom, and we want to bring them together to form a carbon monoxide molecule to see what that looks like. The very first thing is the electrons that are closest to the nucleus, they're happy being close to that nucleus. They don't want to move. They like having those front row seats. Because of that, they're not going to be a part of chemical bonding. They're not going to react with carbon and oxygen. It's going to be the outer ones that are involved in the chemical bonds and the chemical reaction. But also, there are other orbits around the nucleus that don't have electrons. Those orbits are there, there's just no electrons in them. And these orbits are also important to chemical reactions and chemical bonding, so we can't ignore them. Is there a way to get rid of this, or? What's that? How do you do that on Mac?
I think if you change the slides manually,
All right. Thanks. All right, so we have electrons orbiting our nucleus. The inner electrons don't do anything with the bonding, and we have these other orbitals that exist but just don't have any electrons in them. When you create a chemical bond, all of these orbitals are no longer individual to a single atom. They're now shared between the different atoms. Both the ones that have electrons and the ones that don't have electrons. They're now shared between the two different nuclei. The core ones, those ones that aren't involved in bonding, they stay with their individual respective atoms, and they're not involved in that process. So this is what a carbon monoxide molecule in this Bohr model looks like. So we want to probe these molecules with X-rays. That's our camera. What an X-ray does, if we bring in an X-ray, X-rays are essentially really high energy light. And these X-rays that we use, they have about 100 times more energy than visible light. So they're just high energy light. What that will do is it'll take one of these core electrons that's specific to each individual atom, and in our case we look primarily at the oxygen, and it will excite it into one of these unoccupied states. And this process is referred to as absorption. By changing this energy, we can essentially map out all of the unoccupied orbitals that are in our system, and we can look at all the different energy levels of electrons that are not being occupied. Now, these reactions will take place on a catalyst. And so we also have to think, how does the catalyst change this chemistry? Well, the catalyst also bonds with the carbon monoxide molecule as well, and it has the effect where it broadens those electron orbitals. The electrons, they're more broad now. And now, we have our carbon monoxide molecule on our catalyst. We can see these unoccupied orbitals, but we also want to see what the orbitals look like when they're occupied. And for that, this is where we bring in our detector, our camera, and these electrons that are in these outer shells, they can relax back down into that core atomic energy level around that oxygen. Because oxygen doesn't like having an electron around its nuclei missing nucleus. So it's going to be very unhappy until one of those farther out electrons relaxes back down. Now these electrons here are much further out from the nucleus, so when it goes into that close orbit to the nucleus of the oxygen atom, that's going to release a lot of energy. In fact, it's actually going to release another X-ray. And this process is called emission. And we can bring in our camera and we can look at that emission. And when we look at that emission, what we can do, because all of these different electrons around here can relax back to that unoccupied state that was around the oxygen. And so by looking at that emission, we can completely map out all of the occupied electrons around the nucleus. And so with this technique, we can look at all of the unoccupied orbitals and all of the occupied electron orbitals. And this is very important because these orbitals are responsible for bonding. It's these orbitals that change during a chemical reaction. So how we can see they change is how we can monitor the chemical reaction and see what's going on. Here's some example data of what you might see for the absorption or the emission. And the main point here is that with the absorption, it becomes very sensitive to the environment around it. So this is all just looking at oxygen atoms here. But they're looking at 3 different oxygen atoms. We're looking at oxygen, which is bound to our catalyst by itself, with nothing else. We're looking at oxygen, which is bound to carbon monoxide, which is bound to our catalyst. And we're looking at oxygen in carbon dioxide, which is bound to our catalyst. So it's 3 different environments. And we can clearly see all 3 different molecules because they become separated in energy by changing the X-ray energy. So we can clearly distinguish these different species, and during the course of reaction, distinguish species that might exist temporarily on the surface as well. So for the X-rays, that's where SLAC comes in. More specifically, the Linac Coherent Light Source, or LCLS here at SLAC. This is the accelerator. Down over here, here's the 280. So you may have seen the accelerator while driving over the 280 overpass. And the LCLS uses electrons in the accelerator to make really, really high energy and fast X-rays. We have a fast laser pump, so we excite our system really fast, which also means we want to look at our system fast. We want a fast shutter speed on our camera. And LCLS provides exactly that for us. And these experiments take place in the near experimental hall down here. And the X-rays are about just as fast as our laser. So they're about equal timing. So here's our general experimental setup. We're now ready to set up the experiment. Here's our general setup. We have our metal catalyst down here, and we have to make sure it's clean. There's no other molecules around, no poisoning or anything. And then we let in the molecules we want. So again, we're looking at carbon monoxide oxidation. So we leak in some carbon monoxide molecules and some oxygen molecules. They absorb onto the surface or stick to our catalyst. The carbon monoxide sticks as carbon monoxide, and the oxygen pull apart into separate atomic oxygen. And if we look at it from the top, this makes a very well-ordered structure. And I mentioned earlier that location is important, and here we can see the carbon monoxide molecules, they like to sit on top of ruthenium atoms, just right on top of them. The oxygen, on the other hand, sits between 3 different ruthenium atoms on our catalyst. And so there are different locations on the surface. So we have our surface, we excite it with our laser, and then we immediately bring in the X-rays to look at it, and we look at it with our camera, our detector. And by varying the time in between the laser and the X-ray, we can take snapshots of the reaction occurring at different points in time and put those together to make a nice movie. Here's what the system really looks like. It's not quite as simple. And we have our catalyst here inside the chamber, and you'll notice that this chamber has a lot of aluminum foil on this. And I always get a lot of questions, well, why do you have aluminum foil on this chamber? So I asked my wife why she thought we had aluminum foil. And her response was she thought we were too poor and had to build everything out of aluminum foil and duct tape. But that's not the case. The reason is that we need a really clean sample. And that means we have to have really, really good vacuum. The way that we get good vacuum is by baking the chamber above 100 degrees Celsius or above 312 degrees Fahrenheit. And that gets all of the water and oils and everything off the wall. That could contaminate our surface, our catalyst. And so we have to bake the chamber for about 4 or 5 days, and the aluminum is really good at spreading the heat all around, so we get a nice uniform bake. So we have our surface. The laser actually comes in through this box over here. It travels over and into our chamber. And then the X-rays come down this tube here, and they overlap together on the sample, on our catalyst. And we have our detector down here that then looks at the X-rays coming off so we can get our data to understand what's happening on the surface of the reaction, or what's happening on the surface of the catalyst. This is example data here of what we get, what we might look like. And so here we change, this is the absorption data. So we are changing the energy of the X-ray, and we can see clearly a well-defined oxygen and carbon monoxide peak, which is good because we have oxygen and carbon monoxide on our sample. And so we can see that. Again, there's no reaction happening right now. This is before we bring the laser in. And then we excite the system and probe it in time, and we can see there's very large structural changes in the spectra. And by doing this at different times and different systems and conditions, we can start to make a really good movie of what's happening. And first, I want to talk about the oxygen, what we see happening with the oxygen when we take this kind of data. So we have the oxygen in our catalyst, and it's sitting there. It's low temperature, it's happy, no reactions happening. And oxygen, it already likes electrons. Oxygen is electronegative. What that means is oxygen is going to pull a little bit of those electrons from the catalyst onto itself, and so it has a slight negative charge because it likes having electrons around. It likes a party. So we excite the oxygen with our laser, and remember this right here, this the temperature of the electrons really comes into play here because we now have these really high energy electrons, these tidal waves, these large swells of electrons. Well, those electrons are very energetic now, so those electrons can transfer from our catalyst onto the oxygen. Well, oxygen likes electrons, but it doesn't like that many. So now it's very unhappy, and it starts to pull away from the surface. Actually, the bond becomes weaker, and it starts moving away from the surface. But electrons are fast. So that electron will only be in that state for 100 femtoseconds or less. Again, it's the width of a human, the amount, light, that's the time that light travels the width of a human hair. And so quite rapidly, it's going to go back into the catalyst. Well, that oxygen atom has already moved away from the surface. It's lost that electron, so now it wants to be back closer to the surface. And so it's going to bounce back towards the surface, and it's going to start just vibrating up and down on the surface. It's created a lot of kinetic energy. It's now very, very excited. It has a lot of motion, a lot of kinetic energy. You can think of this as a rubber band, where you pull the rubber band away, and then you let go. It's just going to vibrate back and forth. So that's what happens to the oxygen. So it gains this energy very, very fast because of the electrons. Now we can turn our attention to the carbon monoxide to see what happens after we excite our system with the laser on the carbon monoxide. So we have our catalyst, and we heat the system with our laser, and nothing happens at first with the electrons. The electrons don't do anything to the carbon monoxide. So we have to wait a little bit longer than with the oxygen, more like a picosecond, or about 10 times slower. And at that time scale is when you really start to see those electrons heat up the phonons in the catalyst. So now the phonons, the atoms in the catalyst are now starting to move in a concerted motion. Well, that can impart motion onto the carbon monoxide, or energy to the carbon monoxide. And it does exactly that. I mentioned earlier that carbon monoxide likes to sit on top of ruthenium atoms. But with this heating up this phonons, making the phonons faster and more energetic, it actually moves the carbon monoxide down further in between other atoms on the catalyst. And so it's now closer to more atoms in your catalyst. Almost the exact opposite of what happens to oxygen. Here's a top view where I'm showing both what happens to oxygen and carbon monoxide together. Yet before laser, the carbon monoxide sits on top of the atom. The oxygen atoms are sitting between those 3 ruthenium atoms. We excite the sample, our system, and the carbon monoxide moves closer down into the area with multiple ruthenium atoms in our catalyst. The oxygen moves a bit out. Well, you can imagine now the oxygen and the carbon monoxide, they're getting a lot closer to each other. And plus, the oxygen has a lot of kinetic energy, so it's bouncing around. Well, collisions are bound to happen, and collisions are exactly what happens, and that would start to form the beginnings of a bond. And we can see that. When we look at this system, so back to the side view, when we look at the system, after about 1 to 3 picoseconds, even longer time scales, we start to see that these oxygen atoms start to interact with the carbon on the carbon monoxide, and it starts to form a bond. It's not a perfect bond. In fact, most of these attempts fail, but they're at least starting to interact. They're starting to try to form that carbon dioxide bond together, and eventually some of them will make it and move on to carbon dioxide molecules, and the ones that don't will go back to the reactants. And this goes back to the transition state, is that when we have our system, when we look at our data, what we see is after we excite the laser and we have this reactants here, the reactants, they're moving up towards the transition state, but most of them don't quite make it to carbon dioxide and they go back down. And we see this motion where the molecules, the reactants, they're really trying to get over that transition state and they're trying to get there, but most of them don't quite make it. Only the lucky few actually make it all the way down. And we can see this in our data. And this was fantastic to see. Here's a movie of what's happening on the surface. And this is just a few hundred femtoseconds or few widths of a human hair long. And here you have the carbon monoxide molecules sitting on top of the ruthenium, and you have the oxygen atoms sitting in between the different ruthenium atoms. And ignore the bottom, there's some boundary conditions here that make it look like these strange things are happening, but it's not. So take a look over here where you start to see the oxygen and the carbon monoxide. So you can see they really start to move around. The oxygen moves closer. Why did it stop? Okay. The carbon monoxide moves down, oxygen moves up. For some reason it wants me to keep clicking it. And you start to see the beginnings. All right. Well. Oh, so maybe it's laser, so I won't use the laser. But you can see that the carbon monoxide molecules move down, the oxygen molecules move out of their site, up more, and you start to really see the interaction of the carbon monoxide and the oxygen atoms. Now, most of these aren't full-on carbon dioxide bonds. You can see here that these molecules are bent a bit. Carbon dioxide is a very linear molecule. So they're not perfect carbon dioxide bonds, and most of them will fail, but you start to see the formations of these bonds, and some of them will go on and form carbon dioxide. And so we can really take this reaction, and we can see every single step of the way, how every single atom is interacting with its surroundings on our catalyst. We see before the laser, we have the carbon dioxide and oxygen. We fire the laser. The oxygen becomes excited very fast. It takes a little bit longer for the carbon monoxide to become excited, but eventually it does. And then the oxygen and the carbon monoxide start to interact with each other, and we start to get this bent carbon dioxide, which eventually a few of those will go off and form this linear carbon dioxide molecule, a complete carbon dioxide molecule, which will then leave the surface of our catalyst. And I want to point out that carbon dioxide, it's not the most efficient reaction. Like I said, most of these don't actually work. But the few that do, we see carbon dioxide leave the surface. Now, when we first started looking at these reactions on surfaces, we didn't jump immediately into this reaction. This seemed kind of complicated. So first we said, okay, well, let's look at how carbon monoxide desorbs from the surface. And so you have a laser, heat the sample. Most of the carbon, some molecules will come off as carbon dioxide. Most of the molecules do not react, so they stay on as carbon dioxide. And if we wait long enough, they will eventually desorb from the surface as well. And this is the primary product. If you look at the ratio between them, 97% of our initial carbon monoxide leaves the surface as carbon monoxide, versus only 3% that leaves as carbon dioxide. This is one of the reasons why catalysts have such high surface area, is so that you can have these attempts many different times to get better and better efficiency. So when we first started out, we really looked at just carbon monoxide on the surface. We wanted to see, how does carbon monoxide come off the surface? Because now we know what it looks like with carbon monoxide and oxygen. And this, on the right side, is the same data that I showed earlier, just focusing on carbon monoxide and much longer timescales, because it takes a lot longer for the carbon monoxide to come off. On the left is carbon monoxide on our surface at the same time, but without oxygen. And the trends in the data are complete opposites. It doesn't behave at all the same way. Without oxygen, you see the data shifts to higher energy, it increases in intensity. With oxygen, it shifts to lower energy and decreases in intensity. So there's completely different processes going on, even though we're looking at the exact same fundamental thing, and that is carbon monoxide leaving a surface. Well, we can look at that through the following diagram of what happens. I mentioned that oxygen is electronegative. It likes to bring some electron density towards it. It likes to have electrons around it. Well, that's going to make the oxygen molecules slightly negative or polar. Carbon monoxide, it also has an oxygen. So that oxygen atom on the carbon monoxide is going to pull those electrons away from the carbon, because oxygen likes electrons. That's going to leave carbon monoxide polar. The oxygen end is going to be slightly negative, and the carbon end is going to be slightly positive. So when this molecule is desorbing, like dislikes like when it comes to charge. Negative charge does not like negative charge, and positive charge does not like positive charge. So if the oxygen was to face down, you're now pushing a negative oxygen against a negative oxygen on the surface. They don't like that. So it's going to orientate itself so that always the positive charge of the carbon is going to face downward, and it's just going to desorb straight up with that carbon always facing down. Now, without oxygen on the surface is completely neutral. There's no charge, there's no electronegativity. And so even though carbon monoxide is still polar, it's not going to interact with the surface in the same way. It can be free to rotate. It can do a little dance on the surface, rotate, and that leads to some interesting properties that these carbon monoxide molecules will essentially, when they desorb, they'll go above the surface and they'll hang out for a bit because they can rotate. And eventually some of them will leave and some will come back down. And so this was really interesting that we're looking at almost the exact same system with just a few oxygen atoms different, and we see something completely different. And so these reactions, are really trying to understand them on a very fundamental scale, can be quite difficult for this reason. And now I have a low battery. So I'll try to wrap this up here. That's a sign, I think. So what about other systems? So we look at carbon monoxide oxidation, but can we apply this technique to look at other systems as well? And the answer is we absolutely can. And I mentioned two earlier, one are fuels and one are ammonia production. And I'll mention some results that we've gotten in both these areas as well as where we want to go in this area. So the first is fuels, or more specifically carbon neutral fuels. What is carbon neutral fuel? Well, it starts out with biomass. Biomass is some type of organic mass. Could be trees, could be corn, could be some other organic mass. It goes through a process called gasification, which essentially turns that biomass into a mixture of carbon monoxide and hydrogen molecules. This is referred to as syngas. That syngas goes through a process called Fischer-Tropsch. And Fischer-Tropsch is where we make the fuel that we want. And this process can be quite difficult and hard to control. And so we really want to look at this process here at the Fischer-Tropsch to see if we can better understand what's going on. So we did a previous experiment where we put hydrogen gas and carbon monoxide gas on our catalyst. And actually for this one, ruthenium is a very good catalyst for Fischer-Tropsch. And the hydrogen does the same thing the oxygen does. It dissociates into atomic hydrogen, individual hydrogen atoms, and the carbon monoxide stays as it did before. We bring a laser in to react it and see what happens. So we react it, and what we saw was within the first 1 to 3 picoseconds, or 10 to 30 widths of a human hair, we see 3 products already on our sample. We see that the hydrogen likes to form hydrogen gas again, likes to recombine into hydrogen gas and leave, but we also see the formation of hydrogen bonding to carbon monoxide, forming HCO, it bonds to the carbon. And we also see 2 hydrogen atoms bonding to the carbon monoxide to form H2CO. Now this is interesting because these are not stable. This is actually an uphill battle. If you were to look at the energy diagram, instead of going up and then down, it would go up and then even more up. So these are not stable, but the reason why we can make them is because hydrogen is fast. Hydrogen is small. The smaller you are, the faster you are. And so because hydrogen is so fast, it when we excite it after a laser, it moves all over the surface, collides with carbon monoxide, and rapidly forms these products, these HCO and H2CO products. And they will leave our system. And so it's not stable, but we still get it to react. And then again, if we looked much longer timescales, we again see carbon monoxide desorbing. And by this point, if there was any of these on the surface, it would go back to carbon monoxide because these are not stable. So the last one, and this is more of a direction of where we really want to go, is looking at ammonia production. So I mentioned that fertilizers, we need fertilizers to grow food and to feed the world's population. Here's the world's population since 1800, and it's growing quite rapidly. So we need the ammonia production to keep up with this rapid population growth. This process that makes ammonia is called the Haber-Bosch process. It was actually developed during World War I as a weapon, but starting in the 40s, it became commercially available to make ammonia with, and now 80% of all ammonia is used for agricultural purposes. And just to give you an idea of how important this process is, this single process is considered to take up 1% to 2% of all of the world's energy. So this is a very, very important process, and we want to understand it a little bit better. Well, why does it take up so much energy? This is what happens in the Haber-Bosch process. You have 3 hydrogen molecules and a nitrogen molecule, and they react to form 2 ammonia molecules. And this happens on a catalyst. The problem is the nitrogen here. It has what's called a triple bond. It bonds, each nitrogen bonds to the other bond. Each nitrogen bonds to the other nitrogen 3 times. That makes it a very, very stable bond and very, very hard to break. So where we really want to move in the research and the direction is to really take this system and first understand how we can more effectively and efficiently dissociate nitrogen to form these atomic species and get rid of that triple bond. And that'll make the reaction proceed much smoother. But also, usually the only way to get rid of that strong bond is to make another strong bond. So now by getting rid of this strong bond between the nitrogen atoms, you now make a strong bond between the nitrogen and your catalyst, which can also be a problem, because if it's too strong here, it's not going to react. So we also want to understand how can we react then the nitrogen with the hydrogen in order to form different products such as ammonia. And so this X-ray spectroscopy, or this technique, that X-ray absorption, X-ray emission that I talked about, where we can really look at the chemical bonds and the electronic structure on these molecules, is a very nice technique because it allows us to really get a camera right down there on the surface and look to see what's happening. We can absorb activation processes like with the oxygen, where we really give that oxygen a lot of energy. Transition states, we are able to see the transition states. We can see intermediates, short-lived species, short-lived molecules on the surface. We can see how CO desorbs completely differently in 2 very similar systems. We can see competing reaction pathways where we have both H2, HCO, and H2CO being formed. And so it's a really nice technique to really see all of this. And the end goal here is that by understanding all of these processes on a very, very fundamental level, we can start to really put computers to use. And instead of going into the lab and testing them out, we can start to have computers calculate for us what are the best catalysts. The catalytic converter that I showed earlier was found empirically. That is, they tested thousands and thousands of combinations of different metals to find the best combination that works. That took many, many years and a lot of money in order to make the catalytic converter. Well, we want to simplify the process by having the computer do that work for us. Take those years and condense it down into days. The computer can then give us a few, like say, these 5 catalysts will be good for whatever reaction that you want, and we can go and do it in the lab. This will save a lot of time and money. So we have a lot of challenges facing us in the 21st century. We have climate change, we have pollution, and so we need catalysts that really work for the 21st century. We need to design brand new category of catalysts. And to do that, we really need to understand how these reactions work and utilize computers so that we can make design catalysts to fit those needs. I'd like to thank a bunch of people involved in this. This is a very large collaboration spanning both SLAC and Stanford, Sweden and Germany, and I'll point out just a few people. Hirohito Ogasawara, he's a beamline scientist at SSRL, and he's been really the brainchild of a lot of this and done a lot of the work and building up the system to allow us to do these experiments. Anders Nielsen, that's my boss. He's also been really one of the key players in really driving this and putting resources behind it. Jens Norskov, his group has done a lot of the calculations, so we can really, the computer calculations, so we can really understand what's going on. We have Henrik Ostrom, who's over in Sweden. He's been really a big help in getting the conditions for the experiments. Lars Pedersen, also in Sweden, in Stockholm. He also is another theory group that's done a lot in terms of calculating, because these spectra can be very complicated, and so we need help in order to interpret them. And so he does a lot of calculations to figure out what the spectra should look like and help us interpret our data. And then Martin Bayer in Germany has also been a very big help in getting everything going and setting up all of this data. And with that, I'd like to thank you and be happy to answer your questions.
Okay, so, well, thank you very much. Thank you very much. So now we can take some questions. Please, if you want to ask a question, wait until you have the microphone, because this is, there we go. This is being recorded, and so your question won't be heard on the audio unless you have the microphone. So please, who'd like to ask a question?
Thank you. Question number one, did you use any matrix underneath the ruthenium? And if the thickness of the matrix and dispersion would affect the results?
No, for these studies, we used entirely ruthenium. So we have a single crystal. It's 10 millimeters wide by 1 millimeter deep, so it's very much a bulk single crystal. If we were to make a pattern of other molecules or layers of other molecule or of other atoms in there for catalysts, that would definitely change it quite a bit. And that's really where the design catalysts come in. But for more of these fundamental, trying to understand surface processes, we want to stick with the single crystals because it provides us with a very well-defined surface that we can then really understand everything.
Okay, my question is very similar. What is the reason for using this ruthenium? It seems to me you just need a crystalline surface and which can provide the free electrons.
It's a little more complicated than just providing free electrons. And so you also need chemical bonds to the surface. And so that surface needs to have some type of electronic structure to help facilitate the reactions because you do chemically bond. And so I didn't really talk about the metal, but I talked about in the atom how you have these 1s, 2s, 2p electron orbitals. Well, in a metal you also have something very similar. And so what we're looking at are metals that have a D band that can help facilitate that chemical bonding.
Hey, I was wondering, it looks like you don't have that many different atoms at once and that their configurations aren't especially complicated offhand. Why not use a simulation? Where do molecular dynamics simulations fall short?
That's a very good question. So we worked very closely with the Jens Norskov group, specifically on the molecular dynamics simulations. And one of the areas where they fall, where it becomes very hard to use molecular dynamics simulations is with the electrons. And so if you have electrons that are really mediating a lot of the reaction dynamics, that can become increasingly very difficult in order to follow these on molecular dynamics. Another one is hydrogen. Hydrogen is very fast, and so you have to start putting code in there to handle the speed of hydrogen. There was one, when we were modeling that hydrogen reacting with carbon monoxide, the hydrogen was moving so fast that in one step the hydrogen was here, in the next step it was inside the carbon, and then that would cause it basically just to explode, which is very unrealistic. And so that's a very good question, but we work a lot with the molecular dynamics group in order to help solve these problems.
Can I just make a comment on this? Mm-hmm. In this work, there's a very close relationship between the people doing the X-ray experiments and the people doing the simulations. And the problem is that it's not just a simple molecule at rest. It's a molecule that's changing its shape on a femtosecond timescale. And so that's the very edge of the computer modeling of these systems. And so the feedback between theory and experiment here is very valuable. Those guys try and predict different shapes that will occur in the intermediates of chemical reactions. Those make predictions for these emission and absorption spectra that Jerry talked about, and then you see which one is actually realized in nature. So it's all very close communication between these groups that makes this work.
Yeah, that was an excellent point. We work very, very closely with the molecular dynamics team on all of this.
I have a very basic question. I don't understand chemistry very well. When you apply all that power from a laser into your molecule and you're knocking out the core electron, the one that likes to stick as close to the nucleus as possible, why don't you scatter all the electrons which like to go away from the nucleus? How do you direct it so it just knocks out a core and doesn't disturb the others?
It does disturb the others. That's a very good question. And it actually, the disturbing the others, knocking out electrons, is actually the main process that does occur. The process between absorbing and emitting, that happens so fast that doesn't actually affect our results. So what we see is the effect of the optical laser, our laser heating the sample. When we look at the X-rays coming off, that process is very fast, and we're only looking at the X-rays. And so if we were to put an electron spectrometer or something to measure the electrons, we would see a lot of electrons coming off of the system because the X-rays are just knocking electrons out from everywhere. But it doesn't affect our system. And just simply that we don't look at it is the reason why we don't see it.
Thank you. Thinking about your piggy bank at the end, how many different metals are there? You picked ruthenium, and you said the 3 in the catalytic converters. How many more potential catalysts are there in the periodic table that could be studied?
Well, in this case, it's not so much about the number of elements in the periodic table, it's about the combination and the structure. And so I mentioned location is important, and so one is designing certain structures and to optimize how sites that the chemical reactions are facilitated on. Another one is you want to mix metals together, because by mixing them together, you can take the best properties of different metals to really try to get the best types of reactions. And once you start mixing the different metals on the periodic table, your combinations become endless. Because
It doesn't make it cheaper.
no. So a big push right now is to find metals that aren't like rhodium, palladium, platinum, and combinations of metals that are much cheaper that we can use to try to get that same type of efficiency, reaction efficiency.
Today we can grow metal surfaces at the nano level, design them at the nano level. So that's the dream here.
For producing the ammonia, how are you planning to break the triple bonds, or are you trying to break the bonds with the catalyst?
Kind of a combination of both. We're looking at different ways to do it. One way that we're looking at it is to actually first try to react the nitrogen with hydrogen first. Because once you stick a hydrogen on there, that inherently is going to weaken the nitrogen bond. And so one place that we're looking is to do that. For the other study where we already have nitrogen on the surface, that we actually use ammonia to break it apart first, because nitrogen is very hard to break apart. Breaking apart nitrogen on a metal surface, you can do it, but you get very, very low yields. And right now they're a bit too low to do practically with our setup.
So everybody's done. How do you control, or actually, a different question is, do you control the pressure of the gases that you inject into the chamber? And how does it affect?
Absolutely.
the
We
results
absolutely
and
control the
poisoning?
pressures. Yeah, we absolutely control the pressures. The pressures are very important. If you put too much pressure of one gas on there, then you might have the surface completely saturated with one molecule and not the other one, so there's no other reactant to react with. Henrik Ostrom, who I mentioned up on the acknowledgements, he's been very instrumental in that. And so he has a lab set up in Stockholm where he plays a lot with temperature, pressures, to really figure out what the most optimal reaction conditions are. And then we take those reaction conditions and look at them with the X-rays.
Thank you. That was interesting. I just had a quick question. Why is the oxygen so ready to disassociate to go from O2? Like, is it more willing to bond to the surface of the metal?
That's basically it. Whenever you have a bond, so one of the hard things with catalysts are oftentimes the bond to the catalyst has to be stronger than the initial bond, but it has to be weaker than your product. Otherwise, you're going to poison your catalyst, and you're just going to fill your catalyst up with atomic oxygen that's not going to react. And so you have a fine balance between those two bonds. Yeah.
I just have to ask this because my neighbor and I were talking about this before the talk, but when you say you're looking and you see, what is the digital camera takes a picture, or is it just an output of a bunch of signals, or what are you reading to see the reaction?
This is a very good question. So what we have, we call it an X-ray spectrometer because it looks at the light coming off the sample. So when we excite it with an X-ray, they emit an X-ray as well. And those X-rays go through what we call a grating, and that grating separates all the different energies, basically a prism for X-rays. And so we can separate all the different energies of the X-rays, and then we have a camera that looks at those energies. And so we can get the energy of what X-rays are coming off. And so we have a camera to do that, and we actually take a picture. So every shot on there, we take a picture. A 1 megabyte picture, we run at 120 hertz, and so in a matter of a few hours, we take terabytes of data because of this. And then we have to go through and analyze those using a computer, because obviously we can't look at every picture and say, oh, there's a data point, there it is, and then we have to bring it all together. So actually the data analysis is a very complicated aspect of analyzing this data.
Can we see a picture?
I don't have my computer. So fortunately not. But I could show you a picture afterwards. This one right here?
You're from a different generation than I am. When I was doing chemical things in high school, it was blowing things up. You don't sound
That's
like...
the fun chemistry.
Is that the new generation? We don't blow things up anymore because...
Yeah, I suppose. I kind of joke that I'm more of a chemical physicist at this point than a chemist, but because I'm looking at just 2-3 molecules at a time. But yeah, I don't see too many explosions anymore.
I guess you're blowing up very small things.
Yes.
Okay. Maybe that's a good place to stop. Jerry will be around for a while and answer any questions you might have if you come down here. The people handling the mic are Jerry's colleagues, so they can also answer your questions. And other than that, let's thank Jerry again, and I'll see you in a couple of months. Thank you.